So the title says technical writer, but anybody who knows me, even in the Sylabs sense of things, knows that sometimes I venture over to the dark side. One of the things that I've learned over the years in venturing over to the dark side is that we're not, copying other people's content. We're just repurposing it. So in that spirit, actually this is with permission and thanks to Bob. I'm repurposing this particular slide here because it's really a great illustration of one of the challenges that obviously a lot of us are interested in here at this particular session. And that is basically the idea of how we take, or perhaps how we bring and take, how we bring compute-intensive workloads into Kubernetes-based environments. And there's a lot of motivation for that. And I think, I'm not going to repeat things that have already been said, but I think that, Bob certainly helped to really set the stage very, very nicely. So obviously, in a traditional kind of a context, Singularity containers are a great fit with different workload managers. And in this case, we're illustrating the case with Slurm. This is an MPI application, that can be executed very effectively. We've seen various examples for this. Other likely suspects haven't been necessarily mentioned here today, but they would include other workload managers like Univa Grid Engine, Platform LSF, which of course is now part of IBM, and so on and so forth. There are many, many examples. And actually, those are two that are particularly special to me because I spent about 7.5 years with Platform and about 3.5 years with Univa. So I've been messing around with workload managers for something like a decade. So part of the reason why when we start kind of recontextualizing these compute-intensive workloads within now a framework provided by Kubernetes, there is kind of this, let's call it a tension that potentially exists between traditional workload management and what is available in terms of workload orchestration for more of the Kubernetes kind of a context. So we're going to delve into a little bit of an example here today involving Slurm, although pretty much everything that I have to share could be extended and related for a different workload manager. So many of you in this community are quite familiar with Slurm. This is a high-level architecture slide that I have also repurposed, but with acknowledgement from this a SCED-MD site. And you're going to see some examples of output from some of these Slurm commands through the demo that I'm going to share with you today. So certainly there's the kind of, I guess the relatively speaking, simpler use cases that are causing us to want to take fairly traditional HPC applications and perhaps reimagine them in a Kubernetes context. And then people like Greg Kurtzer have talked a lot about enterprise performance computing as well. And basically that is, simply stated, an extension of requirements that are very much analogous to that which we have been focused on in the HPC community for many, many years, now into the enterprise. And it could include such things as machine learning, deep learning, AI, et cetera, and so on. However, and this is of course another repurposed slide, I thank Greg for this one, we also are seeing these very, very interesting hybrid use cases emerging. Hybrid in the sense that they are combining requirements that are traditionally, set out in typically, compute-intensive HPC kinds of contexts with additional kinds of requirements. So, basically what you can see here is a need to have containers at the center of a solution that needs to take into account streamed workloads, data streaming at potentially at very, very aggressive rates. You need to funnel that in real time into various kinds of applications and perform various kinds of, sort of more machine learning, AI kinds of, deep learning kinds of tasks and so on and so forth. We've actually, if you think about it, over the last couple of days, feels like the last couple of days, we've actually seen some examples of this from other speakers here at the conference as well. So I think this kind of sort of generic use case is becoming increasingly interesting. And we've basically mentioned here a number of the different technologies that come into play here. Now, Michael's already covered some of these points here. These are just in here as slides for completeness. So you've already heard about a little bit of the context that we're framing this in. You've heard about the fact that we have a alpha release of the Singularity Container Runtime Interface that's now available via GitHub. You can actually go ahead and clone that and start working with it. And we really would encourage you to do that, because that's how all of this stuff just gets much more valuable and it gets much improved. So the challenge then, or one of the opportunities that can be presented in a context like this is we could have taken, sorry, from a high level, what we've got here is a native interface between Kubernetes on the one hand and the Singularity runtime on the other hand. And so really what this Singularity CRI turned out to be is a gRPC server implementation. That's really the focus of our CRI work. And that allows a kubelet, as you can see from this graphic here, which by the way is also repurposed from a Kubernetes blog post, that would allow us to effectively spin up a container, kind of a nice, appropriate one-off offering. But we'd like to take it a little bit further than that. So I alluded to the gRPC capability, and again, there's just a little bit more detail here. So as I think about this, I'm taken back to 2003 when I contributed a paper with colleague Chris Smith at the time. I was working for Platform Computing, as I alluded to before. The book was called Grid Resource Management. And to keep vendors like Platform in check, what we were given was basically an emerging specification from one of the standards bodies. I can't remember if it was OGF or GGF, but certainly something of that ilk. And the spec was all about metascheduling and scheduling as sort of described through the lens of scheduling attributes. The idea that if you have some kind of a workload manager, in this example, Platform LSF, functioning at the cluster level, and that you wanted to perhaps be looking at scheduling from a grid computing perspective, that there was this other meta level that needed to be concerned about. And lo and behold, don't we start hearing about metascheduling again, this slide repurposed from Greg Kurtzer, where we are now at the point of, in some sense, revisiting that, now in a Kubernetes context. And basically, what I want to show you here and to talk about in a little bit more detail and see if it generates some interesting dialogue is how we have actually now started to build this interface between Slurm in this particular example and Kubernetes, and actually give you a quick demo of that. So this is a schematic of the integration work that's been done. I'm shamelessly leveraging work that's been done by one of my colleagues, our colleagues, Vadim, who's over here on GitHub. I mean, in spirit, he's not live or anything like that. So this is actually work that is currently going on in a private repository, but we will be making this available to the community in due course. We don't really, that's apologetically a bit fuzzy, but it is something that we were actually actively working on. And so what the schematic illustrates here is that Vadim has been doing some work to help facilitate this integration between Slurm on the one hand and Kubernetes on the other. He's built a number of different components, and I'll go through each of these in varying degrees of detail here. So one of the key components is this Slurm controller here, which is implemented as an interface layer between the work that we have done and implementing other components, and Slurm itself. So you can see that each of these sort of functional blocks here represents a particular node. It's interfaced with the master part of the Slurm service, which I showed in the previous sort of pure Slurm schematic here. And then we have these other additional components which play different roles here, and you'll see why we need these different components. So in this diagram here where it says job container, this should, there's a little bit of a typo here, and I'll address that in a moment. And then the other piece here that we're talking about is something called a resource daemon. So the controller, which I mentioned before, as you can see, is essentially a fairly simple HTTP-based interface for accessing the Slurm commands. So that's how we're actually interfacing with Slurm, as opposed to, you know, some other mechanism of doing API calls or anything like that. So this gives us access to some of the standard Slurm commands. You're going to see this in the demo in a moment. And basically, this allows us to implement the basic job control characteristics. And again, as I was mentioning before, this current implementation is very specific to Slurm. However, in principle, this could be applied to any other workload manager, WLM. The job daemon, so this was the one that was kind of a little bit mislabeled here. We called it a job container here. This is, sorry, each of these is actually a Singularity container here. And the job daemon, so this is some of the work that Vadim has been doing. He's implemented this, of course, in Go. And this is a new piece that gets inserted into the Singularity container, and it handles communications with the Slurm controller. So this is really, you know, if in many ways, the kind of the handler for the job. So I think of it as being analogous to the daemon that is responsible for kind of managing workload in a traditional HPC computing context. And of course, it's completely out of band from the user perspective. Now, from the user perspective, the user experience, and you're going to see this in the demo, basically you make use of kube control, a command line interface that's provided with Kubernetes to do all of the sort of the job management kinds of things, as we'll see through the demonstration. And then you can see that there are some additional details here that are part of the implementation. You can make use of a CIF container, again, of course, or a Slurm batch script. And basically, what happens here is that a pod gets started, and then the job daemon is able to communicate with the Slurm controller. To make sure that everybody is in sync, because this is actually one of the difficult challenges, there's that resource daemon component that appears in the schematic here, the RD part. So one of the challenges, of course, is that if you think about it, and again, if you think, sorry, I'm going to go way back here to this slide here. I mean, in the traditional HPC context, typically the way that these kinds of HPC clusters are set up is that you've got a workload manager like Slurm has dedicated access to compute nodes, and it tends to be a fairly static environment. I mean, certainly there are changes made and so on, but it's not the highly dynamic world that is more typical of the services-based environment. But even communicating updates on what is currently available is an important part of the consideration here. So this resource daemon is essentially has been implemented to keep the Kubernetes environment apprised as to the resources that it has available. So there's this ability to do ongoing communication here. And as you can see here, we are making use of node labels to be able to characterize devices, plugins, and architectures, and then the extended resources capability to take care of other things such as CPU, memory, and so on and so forth. So, the demo. Now, again, in a fairly conservative fashion, there was the Canadian reference earlier after all. Let me just see if I can find my movie here. We'll go ahead and start this off at the beginning. And let me make this nice and large. So we're basically making use of Minikube, which is a way of providing a Kubernetes environment in a nice, locally usable fashion. So if you care, version 3.5. So that's one of the, hopefully you guys can see this. Anyway, this is, we just issued a basic command from the Slurm perspective to give a sense as to what's available in terms of the partitions that are able to receive workload. What we're showing here is accounting data from Slurm. So this is showing us information on a job that has already completed execution because we're going to launch a brand new job. So via the kube control command, we're finding out which pods are currently active. So these are basically some of the components that Vadim has actually been developing, and this is the kind of stuff that you will eventually see appear via GitHub as well. He's created a submission example using YAML. And so fortunately, people like Bob went over this before in terms of kind of the high-level perspective as to how we're using things here. What you can see is that we're going to pull from the Sylabs cloud the very famous LOL cow container. We're going to run it, and of course we're going to run it using Singularity, but also via Slurm, and then we're actually going to remove it. So this is kind of a complete, this is really a workflow that we have that's described here. So we'll let this carry on here. Oh yes, and of course, forgot that there was this highlighting. So Vadim is just highlighting the pieces that I have already kind of more or less spoken about. So there we go. So what we're going to do now is we're going to basically apply this configuration, and then you can see that indeed now we have a new cow job pod that has been created. It's a very, very short running job. You'll see it appear in the logs here in just a second. So these are, of course, logs from Slurm, and in fact, what Vadim is going to do is highlight that we have just executed job number 33. You may remember when I started, job number 32 had already happened. And what you can also see are, in fact, those other pieces of the workload that are included here. And so now if we issue the kind of the Slurm accounting command, you can see that job number 33 has also completed. So this is a complete demonstration to show that this is actually a real example here. And then I believe finally here, you can see the output that was produced by running that container. And there it is there, of course, the extremely famous LOL cow, which is becoming the rapidly becoming the canonical use case to demonstrate the most basic functionality from a Singularity perspective. Which I already mentioned the YAML stuff. So how am I doing for time there, Chair? 1 minute? Okay. So I will just throw out here very quickly that the folks over at Univa have actually also, because Bob mentioned or alluded to other possibilities here, they've also delved into the water here. This is the generic architecture for Kubernetes. Bob talked about the innate capabilities of the Kubernetes scheduler. The folks at Univa developed a product called NavOps Command. Basically, what they literally did in a simple way is they took the smarts of the grid engine scheduling capability and they stuffed it into a container. And so there are other exemplars out there that are pretty interesting and worth discussion. So in summary, what I just want to emphasize is that what we think we've done here is integrate with Kubernetes in a very complementary way. We've taken the existing container runtime interface implementation that's now at an alpha preview, leveraged that in now providing an integration with Slurm, and hopefully there will be something we can share with you in the not too distant future. And we think this is very exciting and very interesting because there are, of course, many compelling use cases that are already emerging. And I think with that, I'll better stop talking. It's okay? I got 20 seconds? Well, I could keep going.
I'm sure you can burn that up.
Yeah. So do we have time for one or two questions? And I will call upon Michael to please give Michael a microphone too. Oh, actually, well, maybe not yet, but he'll be, he's going to have to help me out here. So we have a question up at the front here.
Thanks. If you go back to the architecture where you have the nodes and the Slurm, yes. So here you have a Slurm controller on each node.
That's right. Yep.
Because normally you have the Slurm CTL daemon on the management node.
Right. So that is basically, that is the management node. What we haven't given you any additional detail on is the rest. So there could be, you could have multiple nodes available.
So each node here is really representing an individual Slurm cluster.
Yeah.
So this is so node 1 here is the physical master node of a Slurm cluster backed by an entire cluster.
Yeah. So it's kind of like having, as you know, to Greg's slide, it's kind of like a meta scheduler for Slurm, because each of these is an individual Slurm cluster. And I probably didn't make that clear enough. So thank you for the question.
Yeah, thanks.
So with that, Kubernetes isn't really controlling this. Sorry. Just want to make Keith run a little bit. So there's not a notion in this case that I would move, say, a given node from Slurm's control to Kubernetes to run some microservices. Or
No, no, no.
These are static.
Yeah, the Slurm the Slurm cluster, it's not so easy to say, is it's a static entity. But I think Michael wants to add something.
Well, I was going to say you could theoretically install just the standard CRI on and the kubelet on every node in one of these clusters. And if we go to there's a picture somewhere over here of this API spec, right? If you just submit a standard deployment to Kubernetes, and you have that just a standard CRI, the Singularity CRI, on all of those nodes, they will still function as nodes in a Kubernetes cluster. So you could theoretically maybe work something in there in that way.
So from the Kubernetes side, if we query how many containers are running, we won't get to know because the Slurm is running them. Is that right understanding? Or
Well, but I believe that what I demonstrated through the demo was that when you issue the kube control commands, you find out what's actually running.
So part of if you go,
You want to do the demo?
no, go to the here. Just go here. It's probably.
right, that was is it a pod or?
Thought it was pod.
So it's a pod here, but it died really quickly in the demo just because it's just running lolcow, which just prints something on output and then dies. But if we had a long running job, that pod is actually going to be communicating status about the running job back through so that you as the end user on your node can then, just by using kube control, you can see the information and the status of a running job, and you can attach to the logs in the same way you would attach to the logs of any other Kubernetes job.
Okay.
Yeah, so you can see here, right, the cow job is still running. Theoretically, if we were really quick, here we could attach and watch that job
And there are ways to monitor what's happening in a Kubernetes environment quite dynamically, so you can see that stuff coming and going.
So I can interleave these then, right? I could have a pod that starts up some web service front end for me and a Slurm job that goes and runs and interacts, and it all just looks like one pod. That's essentially the... Am I getting this right?
Maybe. I would actually need to look into that. I'm not sure about that,
But
from a technical point of view.
But from the use case that you just described, Andrew, why can't I find it? That's exactly the direction we're trying to head in, right? And, I think that my colleague there, Ryan from Down Under, you pretty much presented a use case that was kind of getting along these lines, right? Yesterday. So this is what we've got here. This is, again, this is Greg's slide. It's just genericized. But as I say, there were several examples that were pretty darn close to this in terms of implementation.
Normally what the meta scheduler does, you submit the job there, and it passes the job to the HPC
Yeah,
cluster or
yeah.
whatever.
Yeah,
And
I
then
hear you. I know.
The cluster takes full control of the job. So who controls the job here?
We still control the job.
Yeah.
Right. So the pod that lives and is acting as sort of a gateway between the Slurm and Kubernetes' API can control the job. So you could still kill the job. You could still, do whatever you want to the job, right?
It's not a true meta scheduler in your sense. As I mean, we have people from Globus in the audience here, so that use of the term might be a little bit too loose for some of those folks, right? This is not a meta scheduler in that sense. It's kind of it could be heading in that direction. No, that was supposed to be positive.
Yeah, I mean, sort of to that point, my question would be, so are the only jobs that are visible via kube control the ones that were started from kube control? Like, for example, what if you had existing jobs running on that Slurm cluster onto which you scheduled the...
Yeah, I mean, the thing is that unfortunately I don't have that. I don't have any data on the job while it's running from the Slurm perspective. However, that job was assigned a Slurm job ID. Right? So it would be visible from the Slurm perspective as well.
Right, but I was curious whether it would be visible from, whether the only things visible to the cube perspective were the things started from your...
Oh, yeah, yes, yes, absolutely. That's the way the implementation is currently.
Okay, so in some sense that might be misleading if you're trying to look into the guts of that Slurm cluster and there's other stuff running that you don't see.
But at the same time, so the resource daemon, there's a resource daemon, right, that lives on these nodes, and that is gathering information just from your master Slurm controller anyway. Right. And so if there are jobs running that are sort of outside the context of being scheduled from a Kubernetes way, those will still be reported as like these resources are not available right now. And so Kubernetes won't even attempt to schedule it if it doesn't have enough resources available in that case.
Okay, that was my question, whether it lived on the node or whether it was actually basically built into the containers that you were doing so it didn't have that visibility.
Yeah, I got it.
Last one. Yeah, I know. That's dangerous. So one quick question. One of the cool things about pods is when they randomly crash, it gets restarted for me. Are you guys reading the Slurm exit status to see if my MPI job crashed and then restarting it if it did? Or could you? Because that's actually a really compelling use case, right?
Is that
no comment.
We'll get... I was going to say, he'll get back to you.
Sounds good.
Great question, guys.
No comment.
Ian, thank you.
Thank you. Thank you, Michael.
That was good, man. I like that. Hey, you completed it. That was so